Do you remember that SNL sketch from the 90s with Will Ferrell where he plays Harry Carey and he's interviewing someone and he's like, what's your favorite planet? Mine's the sun.
I do. I forgot about that, but I totally remember that.
He's like, I like it like it's like the king of planets.
It is the king of planets. It's like most of the mass and most of the energy in the solar system, and it determines the course of everything that happens. It's the king of the planets.
Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hamlin.
And I'm Nancy Bompey.
And this is Third Pod from the Sun. Hey, Nancy.
Hi, Shane.
So, we're talking about the sun, and I wanted to know, what are your least and most favorite things about the sun?
That's a good one. Let's start with least.
Okay.
Least is when it's hot in the summer, like it is right here now in DC, and so hot you can't even bear it, right? Like when you,
No, that's fair.
walking to the office and you're already drenched in sweat.
I'm with
So
you.
least.
Okay.
Favorite though. A lovely sunset.
Oh, look at that.
Yeah, I mean, it's pretty. Actually, that is one of the things. I mean, in our daily lives and thinking about the sun, that's like it's so beautiful. Sometimes the sunrise, the sunset. It really, stop and take a look and take a picture.
That is so lovely, Nancy.
And having a drink on a beach, maybe.
All right, so today we wanted to bring in our producer, Liza Lester. Hi, Liza.
Hi.
What do you got for us?
I talked to Dan Seaton. He's a physicist who studies the sun and the sun's atmosphere. And he wants to understand the weather that's coming from the sun. So not like heat waves, but things like solar flares and coronal mass ejections, or these big bursts of particles, charged particles that come off the sun. And they can hit us here on Earth and cause problems with like our power grids and our satellites and GPS systems and things like that.
I remember there was a point I had no idea what a coronal mass injection was before I worked for HEU, so this will be exciting. All right, so here's the interview.
I'm Dan Seaton. I'm a solar physicist. I work jointly at the University of Colorado in Boulder and at the NOAA National Centers for Environmental Information, where we really sort of process all the data that comes down from various NOAA spacecraft that observe the sun and the heliosphere and the geosphere. So the heliosphere is sort of all the stuff from the sun out to the edge of the solar system. And the edge, even beyond the edge of the solar system, the planets, like Voyager, which has been traveling now for 40 years, is just sort of leaving the heliosphere and going into interplanetary space. And what happens is the solar wind sort of pushes out and forms a bubble of a sort of electrified magnetic fluid that fills all the space between the planets. I mean, we talk about space being empty, but it's not really empty. There's stuff. There's not much stuff, but on big scales, on planetary scales, there's a lot of stuff. And that's the stuff that we're interested in for space weather, because that's the stuff that determines sort of what's happening in the around our planet that can interact with our magnetic field and cause a lot of interesting events. I try to sort of untangle, by looking at the images we produce, that mystery of, how do you take forecasting the next step, and instead of just watching something happen on the sun, like forecast that it's going to happen before it happens, but we're not there yet.
So there's actually weather in space. What is weather like in space?
Yeah, I mean, obviously it's not the same as Earth weather. It is in a sense. I guess it's analogous to Earth weather. Like there are storms, and there are fair weather days and bad weather days. But I mean, the basic idea is that outflow from the sun, so charged particles moving at high speed, and the magnetic fields that get carried along with them sweep out from the sun over the Earth, and they can interact with the Earth's magnetic field. They sort of shape the Earth's magnetic field. You've seen comets with comet tails, and that's the same phenomenon, pushing the comet tail away from the comet, as is shaping the Earth's magnetic field. That sort of makes it into a tail, and the solar wind's buffeting the Earth on the sun side and then stretching the magnetic field out into sort of deep space on the other side.
Now I'm just envisioning some sort of like clip art illustration of like magnets in space.
Of the magnetosphere? Sorta.
I guess.
Sorta.
Well, then what is it, Nancy?
So it's the region up above, out in space, above the Earth, that is dominated by the planet's magnetic field, by our Earth's magnetic field that's generated deep inside the Earth.
So this magnetic field, it's stretching out really far around the Earth, like above our atmosphere.
Yeah, so on the sun side, it goes out to like tens of thousands of miles, and it sort of provides us a bit of like a protective shield from the oncoming solar wind. And on the other side, it stretches out really far because it's pulled by this solar wind sweeping over us. So it's, I don't know how many hundreds of thousands of kilometers into space. When you get a lot of stuff, like a big solar eruption, then you get all sorts of crazy effects. When you get fast-moving stuff, like sometimes there are fast-moving streams of the solar wind that sweep out at 700, 800 kilometers a second. That induces, again, weird changes in the Earth's magnetosphere that can put satellites in danger, that can put astronauts in danger, that can cause all sorts of secondary effects on the Earth, interfere with communications and cause power outages. And so we're doing weather forecasting to try to prevent those things, just like, the Hurricane Center does weather forecasting to try to, well, you can't prevent hurricanes. You can't prevent these events either, but you can be prepared for them.
You were trying to find out when weather will happen on the sun.
And,
And how that will hit us here on Earth.
Yeah, the hardest part is the sun, right? Like, we don't know anything about the sun. I mean, we know a lot about the sun, but we're just scratching the surface. And so trying to say, okay, we're going to look at the sun and we're going to forecast some event on the sun is next to impossible. We see events, and then what we can do is forecast how they're going to impact the Earth, or whether they're going to impact the Earth, whether they're going to propagate in the direction of the Earth or go harmlessly out into space, how significant they're going to be, how energetic they're going to be, and then that kind of correlates to the kinds of effects you can expect to see on the Earth. That's space weather forecasting in a nutshell. Like, on Earth, you watch satellite video and you run these models and you say, oh, we see this little tropical wave forming off the coast of Africa, and we can predict that in 2 weeks it might be a hurricane that's going to be a problem. But we don't get that. I mean, the best case, you get a couple of days of suspicion that something could happen, and you still don't know when or how.
How much warning are we talking about here?
Well, it's not much. I mean, some of the space weather effects that you get with a solar flare happen the moment that the light from the solar flare gets to the Earth. So that's 8.5 minutes. And, the flare happens. 8.5 minutes later, the light gets to Earth. That's the first chance we have to see it. And instantly it induces changes in the ionosphere that can cause radio blackouts and stuff.
Wait, hold on. Okay, we talked about the magnetosphere and the heliosphere, but what's the ionosphere? Like, I'm picturing like a sphere of ions.
I mean, not that far off, I guess, maybe. So it's the upper layer of the atmosphere, and the gases in that layer get excited by all the radiation coming off from the sun and forms ions. So ionosphere.
All right.
But the ionosphere is also cool because you can bounce certain kinds of radio waves off it. So like AM radio, which maybe you've never heard.
I've never heard. Not that young. Jeez.
But also like shortwave radio, like the kind that ham radio operators use. They use that to bounce it off the ionosphere, and that's how you can hear it on the other parts of the world. Get the radio waves to go that far. But if the ionosphere is really charged up, if things are really exciting on the sun, then it absorbs these radio waves instead of bouncing them back, and you can't have radio that way.
The ionosphere is sitting between us and like all the satellites. They do GPS. So if the GPS signal is coming through a ionosphere that's not what's expected, it can get distorted. And so you can get like a bad reading on your GPS. So like, if you're like driving a car down the road and you get bad directions, it's not necessarily that big of a deal. But like planes rely on GPS, and ships, and really importantly, search and rescue relies on GPS. So like, I mean, there's like a lot of significant risk if there's interference there. There's other effects. There's old school navigation technology used by boats out on the ocean that bounces signals back and forth between antennas that are on the land. I mean, that stuff can get messed up. And so there's a lot of potential impacts that you might not think of. Then there's also effects that take a few days to get here from the sun, and those are easier to forecast. So like a power outage that is spawned by a space weather event, we usually have a pretty good idea of that event is coming. We don't always know how serious it's going to be until we get here.
As an ecologist, I had no idea what the heck space weather was. It doesn't rain in space.
No, not really.
Let's back up just a little bit first.
Sure.
Describe a flare to me. What does that look like?
Yeah, they're really dramatic, impulsive explosions. I mean, flares, by their definition, are just brightenings on the sun. They're very rapid brightenings that we see in X-rays. But, we have images where we can really see the sun. You don't just measure the amount of light. You see all this dynamic stuff. When we look at the sun, we can really see the actual sun's magnetic field sort of traced out in the plasma that's in the sun's atmosphere. So the same thing that people see during a solar eclipse, we see with satellites all the time, not just during a solar eclipse. And so you can actually see the sun's magnetic field, and it changes configuration, and you see big flows of material out into space. So flares are these really dramatic things, and they set in, and then they kick stuff off into the heliosphere, and then that's stuff that is interesting from the space weather perspective. These ordinary flares, they maybe have a brief impact on the ionosphere. They get bright, but they're just a quick little blip. Just something gets bright on the sun and it goes away in a few minutes or an hour or something like that. But these big flares, like the September flares, reconfigured the sun's entire atmosphere. I mean, they launched these shock waves that propagated all the way around the sun and bounced back off of each other and just scrambled everything. They threw huge amounts of stuff out into space. They heated parts of the sun's atmosphere up to 30 million degrees. I mean, outrageous temperatures, temperatures that are hardly real. It's so hot. What is 30 million degrees? You get amazing data. You see so many effects, physical effects. You get a chance to test exotic theory. I mean, these flares act as particle accelerators. So, this is like a physics lab at the same time as it's, a driver of space weather, science, research, or whatever. So, yeah, the really big flares are really special.
What's the biggest flare ever recorded?
Nobody knows. There was a really big flare in the mid 1800s, which is called the Carrington event, and it was so bright that you could see it in white light on the sun, which is not normal. That doesn't typically happen. Flares, they make a lot of radiation, but it's generally in ultraviolet and X-rays. And to actually increase the brightness of the sun takes extraordinary energy. And this thing touched off huge geomagnetic storms. These things, set telegraph equipment on fire, telegraph offices. Yeah, it caused aurora so far south that it never happened again.
All right. So this Carrington event was a really big deal, but it happened a long time ago. Almost a couple hundred years ago. Has anything like that happened since?
Yeah, it has. It's happened. And actually, last September, there was a pretty big event that happened.
So early September 2017. This was an exciting time for space weather. Also a bit too exciting for some places on Earth.
Yeah, so in September, the sun had been very quiet for a long time, but suddenly in September, this big, what we call an active region emerged on the sun, this big, complicated mass of magnetic field, and it causes sunspots, which are big, dark things you actually see on the surface of the sun, and causes lots of radiation. And anyway, this thing produced two huge solar flares, the biggest solar flares we've seen in more than a decade. And both of those solar flares just happened to occur on the sun at a time when the sort of, part of the Earth with the Caribbean was oriented towards the sun. And if you think back to September, you remember it was this horrific hurricane season in the Caribbean. I mean, they just kept coming, big ones, bad ones. Hurricane Harvey had recently passed over, and then you had Irma coming through, moving up through the Caribbean up to Cuba, and then Jose, which was a little further north. And a lot of these islands maybe they had weathered the storm, and now they're trying to figure out what's coming next. Do we have to prepare? They're relying on radio networks run by amateur radio operators, for instance. And so just as these hurricanes were sweeping over various islands in the Caribbean, big radio blackouts happen. Now, for emergency response, a big widespread radio blackout might not be that big of a deal because they don't usually use the kind of communication technology that relies on this, use of the ionosphere to bounce radio signals. But imagine that you don't have cell service because all your cell towers are either without power or knocked down. You don't have telephone wires because they're all knocked down. You don't have electricity. You got to get messages through, and sometimes you got to coordinate with, disaster relief that's on the, mainland of North America. And you got to get information to people like weather forecasters who you may not be able to get to the, their normal like sources of satellite information or whatever. And it happened twice because there was one big flare on September 6th and then another one on September 10th. And both of those caused problems. And it's a reminder that like you got to look at the whole picture, including what's happening on Earth and globally around the Earth and space, if you really want to understand, the impacts of like major sort of national scale potential disasters.
So I had no idea that this was happening. Like we just live our daily lives and there's like solar flares.
Yeah.
Everywhere.
Flares like happen all the time.
All the time.
All the time.
There's
Well, not all the time, but they happen.
Is there one happening
And
right
you just
now?
don't even know about it.
What is making, why does a flare happen?
That's a really good question. We sort of know. So what happens on the sun is that basically the sun's magnetic field is entwined with the plasma with the gas, the sort of electrified gas that makes up the sun's atmosphere, which we call the corona. And over time, the motions of the fluid in the sun, because the sun is not a solid body, it's a fluid, it's boiling and churning away. And each little motion of the fluid in the sun sort of twists up the sun's magnetic field. It's a bit like if you twist up a rubber band and you twist it and you twist it and you twist it, and then all of a sudden it kinks. This can happen in the sun's magnetic field. It gets twisted and stressed and stores up all this energy, and suddenly it reaches the point where it can't maintain its equilibrium anymore, and it can kink. It can actually kink. We have movies of this happening. Or it can explode out into space. Where this deposits huge amounts of energy into the sun's atmosphere. So much energy in big flares, it's like if you add up all the energy produced by humanity since the beginning of humanity, it's that much energy, more than that much energy in a matter of seconds. So, yeah, big stuff. This process can accelerate particles, so like protons and electrons and that kind of stuff, to almost the speed of light. And those things, they generally go out in all directions, but they can come streaming towards the Earth, and they can run into the Earth within a few minutes of the time we see the flare, to a few hours, depending on exactly how fast they're going. And those things are really hazardous. Like if you're an astronaut outside of the International Space Station, you do not want to be there when suddenly there's all this radiation coming at, very high energy. And so one of the next things that has to happen is like if we see a big event, like NASA would take some steps to protect astronauts, that kind of thing. And it can also impact satellites, cause satellites to fail or to have weird, computer problems or whatever. And then after that, there's stuff that gets kind of, blown off the sun. It's not gradual, it's thousands of kilometers a second sometimes, but it's not the speed of light. And this is a sort of a big cloud of magnetic field and ionized plasma that sweeps over the Earth. And then that's when you get later effects like power outages and, potentially currents can flow in railroad tracks and warp the railroad tracks. It's crazy stuff as this magnetic field interacts with our own magnetism at Earth. The simplest thing that can happen is it just compresses the sun side of the Earth's magnetic field. And who cares, right? Well, if you're somebody who operates satellites that expect to be inside this magnetic field and protected from, all the crazy radiation and stuff that's in interplanetary space, they can suddenly find themselves outside this field. And in the worst cases, satellites fail because they get exposed to this radiation and they can build up electrical charges inside their bodies, and the discharge can damage components. And, like if you lose your radio on your satellite, then you can't talk to it anymore. It's effectively lost. And that's happened on occasion. That's like the sort of simplest thing. And then obviously there's more complex interactions that can happen. So you can actually strip magnetic field from the front side of the Earth and move it to the back side of the Earth. And then that magnetic field can interact with itself and cause a storm of its own. And that's often the process that actually generates the most damaging effects on Earth. So it's actually the Earth's magnetic field being sort of reconfigured not totally unlike what happens on the sun when a solar flare happens. You store energy in the field, and then you sort of change its structure, and then you release that energy, and then that causes all sorts of flows of particles that can lead to like the aurora, which is, space weather at its best, right? It's like, it's really beautiful and doesn't have a lot of harmful effects, but that can lead to these geomagnetic currents that can like wreck, power grids and that kind of thing.
So it kind of induces these currents and power grids that they're just not prepared for.
Well, yeah, I mean, that's the idea of space weather forecasting. They can be prepared.
And I assume they are preparing.
Yeah, I mean, that's why the science is so actually really important. I mean, if you are a power company, running a power grid, you know about space weather, you're watching, you're working with the scientists and the space weather forecasters to understand what's coming and how you can prepare your grid in case something bad comes our way.
Is there an alert system like we have for Earth weather?
Yep, it's just like we have for Earth weather, like with hurricane categories or whatever. There's and severe storm watches and warnings, flash flood watches and warnings, all that stuff. They have a sort of parallel system that anticipates the primary effects of, different kinds of space weather effects, and categorizes them on a scale of 1 to 5, where 1 is like, don't worry about it, and 5 is like, this is a big deal, you better take precautions. The Space Weather Prediction Center is, I think, staffed by 2 people all the time, around the clock, just like any weather station or weather service office. They sit in a room with like 40 computer screens, and the screens are showing all the information we have available about what's happening on the sun, between the sun and the Earth, near the Earth. There's ground-based sensors on the Earth that can tell us some things. There's like satellites in Earth orbit that tell us some things. And so they're watching, what does the sun look like? Is it active? Is it not active? Do you see a flare? Where is the flare? And then do you see stuff going out into space that could be dangerous to Earth or not? And then there's some satellites between the Earth and the sun, and they're watching little timelines that show, oh yeah, this thing sees a big jump in the speed of the solar wind, which is like one of the best predictors for whether there's going to be a geomagnetic effect. And that also is the only bit of warning that you get that a big geomagnetic storm is going to happen, because the satellite that looks at it is like a million-ish miles away from the Earth.
So it's almost like the wind coming in before a big thunderstorm.
Yeah, you like see this, and then you say, okay, at the speed this is going, we have 30 minutes before this is going to reach the Earth, or an hour before this is going to reach the Earth, so we better be prepared. And then, in addition to all the data, they have models, and the models aren't quite as sophisticated yet as the Earth weather models, but they do a pretty good job of like telling you if something comes off the sun, is it likely to hit the Earth or miss the Earth, that kind of thing. And then they're just like on the phone. Airlines will call them up and say, it looks like the sun's a little active. What's your opinion? And they give an opinion, and they write forecasts. I think they talk daily with NASA for planning activities on the International Space Station. I think it's a pretty busy and stressful job, actually. There have been historical episodes where flares were misinterpreted as like nuclear strikes. I don't know that much about them, but like you definitely want to know the difference between an electromagnetic pulse from a nuclear weapon and a flare, or bad things could happen. And this is one of the services that the Space Weather Prediction Center provides. They let you know, this was just a flare, there's no need to panic. I don't think space weather is the kind of thing that causes the apocalypse. It can cause like a big hassle and an expensive problem, but I don't think it's one of those things that's going to it doesn't threaten civilization as we know it. But but like that, it's a big expensive problem that could be a real headache for civilization, and we're working on solving that.
So Nancy, what are your views on Nicolas Cage?
I don't have a view on Nicolas Cage.
Everyone has a view on Nicolas Cage.
I don't know.
Did you ever see Knowing?
No.
Okay. Oh my goodness. So it's bad, but it's good. Like the world's ending because of solar flares, but it's actually because of aliens, and the aliens are like stealing the children to like put them on another planet to like help them build a better life. But like it's Nicolas Cage and Rose Byrne, and
But they think it's a solar flare?
no, it is a solar flare. Like the
But
world
it's
ends.
aliens.
Spoiler alert.
Thanks, because I'm not going to go see that one.
I know. You're welcome. I just saved you that time. All right. So that's all from Third Pod from the Stun. But stick around to see how Dan thinks the world is actually going to end.
But first, special thanks to Liza for bringing us this episode. And of course, thanks to Dan for sharing his work with us.
And the podcast is also produced with help from Lauren LaPuma, Josh Spicer, Olivia Ambrosio, and Kaylin Camacho. And thanks to Kayla Suri for producing this episode.
AGU would love to hear your thoughts. Please rate and review us on iTunes and listen to us on your favorite podcasting app.
And now, Liza?
So we have this new question we're asking everyone, and it is, how do you think the world is going to end?
Well, I mean, as a solar physicist, I think what's going to happen is the sun is going to increase in brightness over the course of its lifetime. It very gradually is getting brighter and brighter. And in about 1 billion years, it's going to be bright enough that like the incoming energy from the sun is going to be too much to like for the Earth to be habitable anymore. So we have 1 billion years, then we got to move somewhere else. We can move to Mars, maybe. Then, a few billion years after that, maybe at 5 billion years from now, the sun will run out of fuel, hydrogen. So normally what it does is it fuses hydrogen into helium in its core, and that's what gives its energy. When it runs out of hydrogen, it's going to start fusing heavier elements, and it's going to change the pressure equilibrium inside the sun, and it's going to blow up really big. So big, it's going to sweep up Mercury and Venus and probably the Earth, which will already be uninhabitable. But our new civilization, which has moved to Mars, is also going to be in trouble. So then we're going to have to think of another solution. So that's my prediction. I try to be optimistic. I think we're problem solvers. I think there's a lot of things that could go wrong for us, but I think we're going to solve them. You know, like we have solved problems in the past, and space weather is one of those things. And similarly, you know, other problems on Earth, I think we'll work to solutions. But there's some things you can't control, and one of them is like eventually the sun's going to change. So maybe we'll make it 1 billion years, but then we're going to be out of time. We're going to have to leave.
Thanks all, and if the world doesn't end, we'll see you next time.